This is to present my report relating to Ray Salmonella, who you see here and here. I'm sorry I don't have PowerPoint, so I'm just going to talk. The main ideas came when I read James Hawkins about multiple predictions via dendrites causing various effects in cortical mini-columns, which can be seen as little matrices, and how many little predictions affect a neuron. So this is the book, and this is the title of my report. Other neurons are in a similar situation. So the neuron can be affected. Neighbor neurons can be similarly affected. The predictions may just prime the neuron, getting it ready to fire, or if the prediction is powerful enough, or the neuron is already primed, the neuron and fellow neurons may act, and then, for example, we push the computer to turn on the other kind of computer. This action of multiple predictions in parallel and with matrices too sounds so similar to Ray's concept of multiple predictions and his probabilistic view of the world that I just had to write something about it. So this report considers if and how Ray Salmonella's general theory of induction, Salmonella induction, using algorithmic probability would be a good tool for his or other neural organizing. Two other early AI scientists, Marvin Minsky and Oliver Selfridge, also had ideas that are relevant to Hawkins. Minsky via Hawkins map models, Selfridge how predictions are recognized, but I won't have time to talk about that. But I would like to say something about domains. People complain that neuroscientists and AI people don't talk to each other, but they can. Past AI, the historical view, also talks with us. Well, I'm a poet, and if you think AI and neuroscientist people don't talk to each other, you just try talking to poets. But if a poet and a neuroscientist can talk to each other, then you really got something. One reason poets and scientists can and should talk to each other is that while we are in different domains, there is overlap, and the overlap can best be seen in the concept of multiple descriptions, describing things in different ways. This overlap helps us reach into the other domains, so it helps with transfer learning. But Salmonella's work seems to have the most relevance to Hawkins, so this report is on Salmonella's general theory of inductive inference, and in particular used with ideas like that of Hawkins. Here are the overall ways I think it is useful. By helping understand better the little predictions of individual and multiple dendrites using their multiplicity of synaptic connections on a single neuron, by being the algorithmic guide when multiple predictions are used and compared in the basal bottom part of the neuron, and when many neurons act in concert. It's two-pronged. One weighs each individual prediction. The other gives the probability that the predicted event exists at all by weighing all the predictions together. It emphasizes the innate predictive power of neocortical agents and agented areas, which is a somewhat different focus than that of many types of reinforcement learning agents. Resilience and stability, while changing to a new level, is important, but prediction is maybe more important for purposeful activity, according to Salmonella. So he emphasizes this future aspect, and it helps us focus on causes and not just aggregations. Now, Richard Feynman once gave a talk about computing, and one of the first things he did was ask about what kind of computer are we talking about? It's very nice to talk about neural nets, but in every case, we really want to know what kind of computer will have this. What will it do? Now, early computers had one centralized CPU. They had an input tape and an output tape. An input-output tape, or maybe they had one of these things. This is stuff that Ray actually used for his computing in the good old days. So I thought you'd like to see it. But they were one thing. Current computers have register software and memory, cache software for the RAM, software and memory on the hard drive, brought into the RAM, used in varying amounts, lots of parts, memory, short-term, long-term, moves all around. There are instructions for everybody. There are local instructions. And now we have more and more parallel computers, which seem much better to match the neuron view of the brain. Parallel computers would have lots of little computers which have programs and overall programs. So they would make it easier to do Salmonella type induction, which relies on using many problems, that is theories or hypotheses, to predict something. So Hawkins talks about 1,000 brains within the brain. 1,000 brains can have 1,000,000 theories, but never get paralyzed by a tsunami of indecision. This might be a real-world evidence of Salmonella type induction. The codes are already a probability distribution of explanations of something, each of which predicts something with a probability that it will be the best prediction given the situation of the owner of the brain is experiencing. The codes are not random. We get away from randomness. We don't like randomness. Each has a probabilistic weight. Different groups of dendrites or their synapses together provide another probabilistic weight. The main point is that algorithmic probability provides a way to imagine how a multitude of theories can have a logical and useful order. The probabilistic weight gets determined by the code length of the explanation, the shorter, more likely. But you can shorten the length by substituting a single symbol to replace multiple symbols and defining the symbol. The symbol plus definition will make the code shorter, and then you can use that. So we wonder if we can do that with things like Hawkins. So here's your brain. On top, you've got the neocortex, a thin layer like a dinner napkin spread all over the brain. This layer is packed with perhaps 150,000 units of intelligence called cortical columns that are side by side. Though the columns don't have strict borders, they can be distinguished by their separate kinds of actions. And within the cortical column are mini columns, each with over 100 neurons spanning layers. Now, so this here is your little neuron. Here's your neuron, and here's a schematic of your neuron. And as you see, this is the soma, the body of the neuron, and the axon, which sends up information. And then information is coming in from all these dendrites, lots of little dendrites. And this is a large picture of a whole bunch of synapses on a dendrite, all sending little codes up the dendrite that go into the soma. And there's all these little codes. And then there are other codes that get judged that this is the basal part and then the apical part. And then there's also feedback, and the feedback goes out. And Hawkins is kind of snotty about it all because he says this is what most neural nets look like. They really don't have this complexity like this kind of thing. And of course, that is changing. So that's your neuron. Let's see, I pause this. Oops. So Hawkins talks about the action of the individual neurons and the communal action, groups of columns working together. In his earlier book, he used the phrase the memory prediction framework for this to describe it. And in his new book, he describes the idea by saying it's a model. He prefers the word model because it more precisely defines the kind of information that he's talking about. But I think Salmonella would prefer the phrase memory prediction framework because his inductive inference stresses prediction as an extrapolation of past solved problems or other forms of sequence. Actually, I think he'd prefer it's an induction framework because it isn't just prediction. And I'd like to make a note about this for people who have read Paul Vitani and Ming Li on Kolmogorov complexity. They distinguish between Kolmogorov and Chaitin's work, which focuses on defining randomness and complexity of a string. Ray focuses on the predictive power of the string. The universal is his invention, and that's true. So they call Ray's theory the Salmonella prediction theory. I don't think he would do that. It's an induction theory. He also focuses on the inductive possibilities of a string, which is the explanation of a string, which I think is rather overlooked in some ways. His induction can do other things. One, it gives a total probability that something will happen. It gives a probability that something will happen in a particular way. But it also looks at something in as many different ways as you have time for. And I'll try to say more about that. It's different analyses of the same problem, and you get a lot of understanding that way. So meanwhile, Hawkins feels information comes via movement and place in modeling the world. These predictions are occurring via the dendrites with different predictions using similar data analyzed in different ways. They send spikings to the neuron with various amounts of strength. If weak but sensible, neurons may go into a predictive mode. If there's enough dendritic proximal, that stuff coming in the side, to create an action potential spike, the cell spikes sooner if it is in a predictive state. The bottom basal area of the neuron is going to compare the new predictions with old, and actions are based on that. So I was thinking in terms of spiking about using the subsequence, shortening of subsequences. Salmonella writes, one common method of devising short code uses definitions. If a certain subsequence occurs many times in the data, we can shorten the data description by defining a specially designed short code for that subsequence whenever it occurs. The bit cost of this encoding is not only the accumulation of the many occurrences of the special code, we have to add in the cost of the definition. So your sequence has to occur a few times before you can save any bits by defining it. But it may be that we do something like that. You can hear it in the phrases we use, like drumming it into your head, stuff like that. So I'll try to get back to weighting via subsequence again a little later. But I want to talk a little more about sequences and their ordering. I don't have much time, so I'm going to skip right to the universal prior, which is sort of at the beginning of the revisions of data to get a better understanding what a thing is. Why is it important for a brain like neural nets? Now, first, I do want to emphasize that in Ray's theory, the word universal does not mean universality. There are two different things. The universal prior is all the possible descriptions of the universe of a domain using the language of the domain. Now, even so, there are impossibly many explanations extending it into the future. So it is contained by using all the predictions that you have time for, not an infinite number. Right from the start, the prior contains the idea of Occam's razor plus weighted larger codes. And second, right from the start, the prior contains the idea of efficiency based on shortness of the code. The prior in the human doesn't go to zero. The nice thing is the prior is not random. It can be based on the language that is used in the body to describe the data. So you, right from the start, you have something that's simple, and that's going to be the base of your progress of theories. And then you have a degree of merit as the different hypotheses come in. And with this prior, in Hawkins, it's the language of the body, especially language of movement. There is added information, you see, that provides more input. So the body does all kinds of stuff. There's sensory data. The added information is like how many mouths, is it male, female, what are some of the genetic elements? In Hawkins, you want the language to be based on movement and mapping. He thinks that the cortical framework makes a map of where we are. And that also would happen right away in the language because the fetus is moved around as the mother moves. It can hear the mother's heart, and it has its own heart as well. So you've got a fine working prior, simple prior right from the start. Now, Ray had a type of computation called resource-bounded probability, which informs learning systems in the real world. The universal prior here is limited by time, sample size, and domain boundaries. Now, if you could have an ideal universal prior, you would use this Turing machine, you know, that has infinite memory. Your input coming in there to with the information, added information in the programming code and the output, and you'd get the ideal universal distribution. The only thing is you can see with the Turing machine, it has an infinite memory. So it doesn't have to worry about time. We do, but even so, it may get into a loop forever, or it may just halt and you never get an answer. So still we can approximate it. And here are the limitations. You have 4 factors that learning and prediction systems really have to address. That's the prediction itself, the reliability of the prediction, the sample size, and the computation cost. These factors have to be addressed in any real-world learning system. Hawkins thinks dendrites send predictions, many predictions. They send a kind of spiking to the soma, the body of the neuron. So Hawkins is using the analogy of saying on your mark, get set, go, and then other things spike to trigger. So Salmonella writes that the simplest explanation of something tends to be the best, but it's not the only explanation. There may be several that are almost as good. Given new experiences, they may prove to be better. The weights of the individual predictions would then change. an early computer terminology, Ray figured it would be the shortest of the explanation. In everyday use, the concept of Occam's razor is the simplest or the most efficient. I can give an example, the kind of thing I'm thinking of. If you usually have the famous cup of coffee, then even without looking, when you grab a handle, you predict it's a cup of coffee. But there are lots of other possibilities, and as Hawkins might say, your dendrites are predicting many other possibilities, and that's what Ray would say. Handle possibilities, a saucepan, a drawer handle, coffee possibilities, espresso, a flavored candy bar. There are lots of possibilities with different probabilities. Your neurons won't be bent out of shape if you find out it's tea. You can replace your coffee theory with a tea theory. But your dendrites will give a very low spiking to a coffee-flavored sidewalk or a cup without sides. It just would take too long to even think about it. And that's what Salmonella is using in his mathematical formula of multiple explanations. The ideal is the probability of X via machine M, and you are machine M, is the sum of all the explanations from 1 to infinity weighted by their length. In the real world, the probability event you are considering via the neural cortex computer is the sum of explanations you have time to think of. You will not encounter the coffee-flavored sidewalk because it's too complicated. It would take years and years to explain it, and the connections are not going to be encountered in your little synapses in the dendrite. Ray notes that the correspondence between probability evaluation and human learning are very close. Prediction of the future based on data of the past. Prediction alone is of little value. It has to have associated quantitative precision. And both the precision is critically dependent on the quality of the data, and it's dependent on the computational resources available. Now, our parallel computers, if we get into qubits and stuff, may have lots of ability there. And I'd like to add something else he said. One of the main advantages of algorithmic probability use of diversity of explanations. If we are making a single kind of prediction, then discarding the non-optimum models usually has a small penalty associated with it. However, if we are working on a sequence of prediction problems, we will often find that the model that worked best in the past, the shortest, is inadequate for new problems. When this occurs in science, we revise our old theories. You will remember, a good scientist will remember many theories that worked in the past and were discarded because they didn't agree with new data or they were unlikely. So you can make new theories from failed models of the past, taking them apart and using the parts to create new candidate theories. By having a large, diverse set of non-optimum models on hand to create new trial models, algorithmic probability is in a good, best possible position to create new effective models for prediction. Okay, I have very little time, so I'm just going to talk a little bit about weighting and the specific thing relating to Hawkins. This is his imagery of neocortical columns. There's a bunch of neocortical columns, and here's some mini columns. The mini columns, as you see, can be considered like a many-layered matrix in which data gets fed into different columns. Here's some different data points coming in to different columns, and they you can have several codes come in at once. They can activate different columns, and you can have several codes coming in at the same time. So that was kind of what I was looking at, and I'll just describe this. I'm not sure that Hawkins does it anything like this, but it's just an idea. Suppose you have a suite of 9 of those mini columns, each with 6 layers. Suppose 5 dendrites send in codes, which are put in the matrix of 9 by 6. Suppose 2 of the codes share some of the same addresses on 3 adjacent mini columns, lining up 3 adjacent mini columns. Maybe you can use some kind of single symbol instead of 3 symbols to shorten the data, as we've been talking about shortening data. It's more likely and it has more predictive power. Then essentially what this would be is just compressing stuff, and that can then guide the next prediction, because you can put it into a Bayesian conditional structure the way Ray would do. The whole neurocortex would then be considered another large, possibly single row matrix that might be more frequentist type. You vote on what you think is right. And also the neurocortex is divided into vision and poetry, whatever, things like that. So different sections might have different predictions, which would be at the same time. But with the compressing part, where you revise the whole thing and then use that to guide the next step, that was what Ray was developing, which he called guided probability. And this might be an example of that. Unfortunately, Ray died before he completed his writings on this topic, but I hope maybe we can find out more about it. So that's just some various thoughts I had, and I'm running out of time. But another reason I wanted to be at AGI is that even though I'm a poet, they are doing so many, you guys, AGI, are doing so many amazing things and even poetical things. And you're often using Salmonella's work as a useful tool. Ray would be 95 this year, so I really wanted to write something. And I really wanted to thank people at AGI, thank AGI, and would like to drink a toast to AGI, and thanks for everything.